Audience may know more concrete technology than me. Maybe Dr. Das can answer that. Yes. So
They are contributing in the strength of mechanical properties.
I agree. What do you say, Dr. Das? Yes. You got the answer from the expert. Okay. Yes. So you can use for both, for improving the properties as well as for filling. Yeah. So it has dual purpose. Please.
Yeah, recapitulation basically used for to enhance the strength of the concrete. So we cannot say it is only a filler in the concrete. It is one of the
It is both.
maybe the both
Yeah.
filler and additives also.
It is both. Okay.
Sometimes we are using fly ash as a filler,
Yeah.
and sometimes we are using as additives.
Absolutely. I agree. That's fine. Whereas silica fume is probably more of a filler.
Yeah.
Right?
But it is enhancing the properties of the concrete in terms of enhancing the density of the concrete.
Okay. It's an effect or cause.
Yeah.
Is it a cause or an effect?
It is not act as a binder, I know that.
Yes, that's what it is. The effect is it's filling the pores better. Therefore, the properties are better. But it's still a filler, I think.
Yes.
Okay, so I get nods from experts. So my case rests there. Yeah. Yeah, I agree. You're right. Anything else? Yes.
Can you highlight on this chemically bonding?
Chemically bonded, it's a very good question because it's a very good question. What they do, I'll show you how the fiber is produced. Okay, that's in a later. So when they are producing the fiber, they spray it with some kind of, it's called sizing, with up. So that coating on the fiber helps the fiber to bond with the surrounding composite better. So that's where I think we are going in a very different direction, but just because you asked the question, I'm answering this. So the suppliers, they'll say, oh, you can buy this fiber, use it in concrete, use it in composite. It's the best solution you can ever have. But if you don't have proper coating of the fiber, let's say you have sizing, remember, sizing means the coating of the fiber, okay, the sizing. That sizing is compatible, one type of silicone, for example. Silicone coating is compatible with polymer-based matrix, but it's not compatible with concrete. So you use silicone fiber with silicone sizing in concrete, it will just melt. Absolutely melt. Nothing. It won't even last forever. It's just gone. So the sizing is very important. So you have to make sure the sizing is compatible. So chemical bond is enhanced by sizing. So that's one mistake many people make. And then after some time you'll see there's no fiber in there. Even for glass fiber, those of you who are using glass fiber, that's only for shrinkage reduction initially, unless you have a AR glass. Okay, we'll not go there, but everything has a purpose, right? So use the fiber with proper sizing for composite action. Like for perfect chemical bond, we need suitable binder. But all these chemical engineers, they will be able to advise you on the proper sizing and stuff like that. So, and also these are all background material that we like to know and we need to know. But I personally will never design a sizing for a fiber. It's not going to happen because I'm not knowledgeable enough to design that. That's the chemical engineer who will do that. And they are better, they have better knowledge on that. Does it make sense?
Not that the matrix and the fiber there's some chemical reaction between them.
Yes, definitely.
But because of the sizing thing,
That
reaction happens.
that bond becomes even better. Because everything is related to pull-out strength, as simple as that. So if it doesn't bond, even in our reinforced concrete, if you dip your reinforcement in oil and then put it in reinforced in your formwork, and then you place your concrete, it will not have as good, pull-out strength, right? It won't bond with the concrete properly. It will fall off. There will be spalling and stuff like that. Okay? Anything else? Yes.
So when FRP is used as a tube for
Hmm.
infill concrete, how do
You have to put some kind of coating. Absolutely, you have to put some. You have to paint it, something like that. And that's why you want to limit those applications, exposed applications to interior conditions. So inside a building can be okay, but if it's exposed to sunlight, then there can be problem. Yes.
Heard that aramid fiber is very weak in water.
Which one?
Water, aramid fiber.
Which fiber?
Aramid.
Oh, aramid. Okay.
It is
Yeah.
not resistant to moisture.
It's quite powerful.
It is drastically.
That's right. Every fiber has its own limitation. And glass fiber has problems with alkaline condition. So they are now selling AR glass, alkali resistant glass. So there are lots of different types of stuff. Anything else? Okay, so let's move on to the next item, which is structural application. This you should find interesting, at least I do. I like this. Okay, so now we will talk about structure. We need a break or something? We'll continue. We'll continue. In case of structural comparison, we are really familiar with this type of comparison. So this is our favorite, those of you who are faculty members who are teaching, these are our favorite mechanics problem, right? You have steel plates attached to timber, and then you use the modular ratio, and then you find out the moment capacity of the section, things like that. So, can we say this is a composite? It is, because we have steel and we have wood, so that's a composite. What about pre-stressed concrete members? So in pre-stressed concrete members, we normally have precast girders or beams. You place them on site, on the abutments, have your formwork, and then place your slab on top of it. Of course, you must have the shear connectors, which is the reinforcement passing through the interface from this precast beam into the cast in situ slab. Okay, so when there is interface shear, horizontal shear, that would these shear reinforcement will resist the horizontal shear. Okay, so that's a composite. We are familiar with this. So I'm trying to present something we already know. Now if you have steel beams and you have shear studs, those are shear studs. Are you familiar with shear studs? They're just round bars with heads, and they are actually welded here and here. And the way they weld it is, they weld it on site. It's called friction welding. So on site, you just use the gun, and this rotates at a very high speed. So that will cause heat here. It will generate very high temperature, and that will fuse. So this shear stud is welded here with very high speed welding machine. So that friction welding will be because of the heat generated. So it's a very fast process. Time is money in construction industry. So steel girders with shear studs, place your slab, that becomes a composite slab. Aerospace industry. This is where the composites have really started being used. So when we are talking about FRP in reinforced concrete now, say in 1990s and 2000. That's when it really started picking up in civil engineering. But in aerospace engineering, 60 years back, they had composites. So we are adapting aerospace technology into civil engineering after 30, 40 years. If you have, this is a Dreamliner, the Boeing 787 blue, this blue color is composites. So on the body you will see the skin is all blue. So there's a lot of composites in this Dreamliner. Same thing with Airbus 380. They are huge, huge aircrafts, right? They have 2 levels of decks and it seats about 500 or 600 people. It's a huge aircraft. So they're able to make it bigger because of the lighter weight of composite. Okay? So inside this, you will have airframe. This is a real picture of the interior of an airplane. All these are composite stringers. The skin is composite. Almost everything is composite in this picture. Okay? That's how advanced it is in aerospace industry. In civil engineering, not so advanced, not yet, because of the cost. Remember, I mentioned something about performance critical applications and cost critical. This is a performance critical application. Therefore, it is easier to implement more expensive materials in this kind of applications. What about boating industry? Boating industry, they use composites on a regular basis. Actually, 1 or 2 people can just lift this and put it in the water. This kind of boats, very light, very nice, very expensive also. This may be about $25,000. This boat. Okay, so they are all very lightweight. What about the fishing rod this guy is holding? That's carbon fiber. So without knowing, FRP has gone into our daily life in a very big way. We won't know it. But the problem they have is this kind of boats. I mean, boating industry is also very well regulated. So the good companies, they do right thing. They provide the proper fiber and everything, well designed. There are also some, small companies. They try to sell their product. They say it's made from composites. There'll be hardly 1%, 1 or 2% fiber in the whole composite, and it won't work. It can easily split. It can break. So if you are going on a boat like this, you better know swimming, right? And supposed to be joke. You are supposed to laugh. Okay, that's fine. Next time I'll raise my hand before I say a joke, so you know I'm going to tell you a joke which is not funny. Okay. All right. So in cars, again, we have lots of composites in this car body. So the hood, that's in almost all the expensive cars, the hoods are composite material. They are made from composite material. And they work very well under crash conditions. So what they do, they actually do crash tests. I don't know if you have seen any Discovery Channel or something like that. It will show you how they test all these with dummies and with all the instrumentation. And these composite hoods are working very, very well. And that's the reason all the expensive cars are now, even inexpensive cars are nowadays using composite materials. What about a tire? You don't think of composites when you are looking at a tire, right? But tire is a composite material, or composite structure. So you'll have a lot of reinforcement in the tire. And we have a tire research center in Akron. Very, very advanced tire research center. So it's a national center. So they do all these testing for this kind of tire pavement interaction, tire structure and structure. It is composite material, okay? And in case of biomedical engineering, you will see a lot of the, in India we call them artificial limbs, but they are actually prosthetic devices. All these are composite material. They are made from carbon, some are from glass, and so on and so forth. And you will really not know the difference. If you see somebody having this with his bare foot, you will not be able to know that's not real. So they have become so advanced, and they work very well. You can see this, right? He's able to run, or I think it's a long jump or something. He's doing something. So I showed you some pictures. Now what's the advantage? Why should we use composites at all? Okay? Obviously, something that would come to your mind is lightweight. So all these composite materials are very light compared to what? When you say lighter, lighter than what? Lighter than steel for sure. For metals, yes. Compared to metals, it is lighter. But that's not a real, we cannot define something as light or lighter or something like that. So what they do is they define it by specific weight. So specific weight is the, or specific strength, stuff like that. It's based on strength to specific gravity or density ratio. So if my steel has a, let's say, strength of 400, I'm just using a round number, 400 MPa, and let's say my specific gravity of steel is 8. So 400 over 8 is, or 8 by 400, you can do the other way around. It's like 0.05 or something like that, right? If you use the same relationship for composite, the composite strength is 1200 or something like that, maybe 1200 MPa or even 2000 MPa. And the specific gravity of composite is probably 2, around 2, just for ease for calculation, I'm just saying that. So that would be very, very good way of comparison. Do you see that? So for a smaller weight, I get larger strength. That's a very good thing. So we have significant weight reduction and and also high stiffness. Of course, related to weight ratio. Stiffness is likely to be a problem. I will highlight this later. You can add your fiber or adjust your fiber content to make it as strong as you want, or not as strong as it. As in some cases, you don't need that much strength, so you can reduce the strength in those areas. So you can tailor your properties based on your requirement. And we will have in a composite millions, actually literally millions of fibers, right? So 1 or 2 fibers break here and there, no problem. Okay? So that will give us redundant load paths. So no corrosion. So compared to steel reinforcement, we will have very, there will be no corrosion. Actually, that's a misnomer now. They have defined corrosion in a different term, not necessarily the corrosion definition that we are used to. So we will not go there, but let's say there is no corrosion. Okay, so it's give you a longer life and low manufacturing cost as long as you have bulk production. So if you produce a lot of same items with same shape, same size, same properties, then it's cheaper. If not, it can be very expensive. And there is inherent damping, and you can increase or decrease your thermal properties and conductivity. And you can add some additives and make it better thermal conductive or less conductive. You can work both ways. So what are the disadvantages? Cost of the materials is very, very high. That's a limitation. But if I'll give you an example. If you say you have a bridge project, okay? Let's say the bridge project, the whole thing, this embankments and like this earthwork and the road work, everything within the scope of that bridge project. Let's say it costs, let's say 100 units. Let's call it as 100 units, okay? So in that 100 units of cost units, the actual bridge itself will be less than 30% cost of the bridge itself. Cost of the materials will be even smaller, so it may be 10% or even 5%, okay? Because there's a lot of labor involvement, right? So actual cost of material in a bridge project is probably going to be 10% or even less. So in the 10% you have steel, which is probably going to be maybe 1%. So I triple, let's say I triple or make the cost of steel or reinforcement 3 times. So instead of 1 unit, I have 3 units. So the total is now 102. Is that right? Are you with me? So I had 1 unit of cost involvement for steel reinforcement, right? Instead of that 1 unit, this 1 unit becomes 3 because I'm using an expensive material, right? So 99 plus 3 is 102. So you are increasing the cost only by 2%. Maybe you'll save it somewhere in the bridge project, somewhere else. So if somebody says, oh, the cost of material is a lot, then you can, as very knowledgeable, very well-trained engineer, you can turn back and say, relative to what? Okay? Yeah, if you are looking at comparing your cost with steel, steel is like $2 or 2 units, let's say, and this is probably $10 or $15 or even $20, 10 times, okay. But in the whole scheme of things, you will see in the whole project, the added cost is not 10% or 20%. Does it make sense? And then I do a lot of research work for my Department of Transportation. They give me a lot of money to do research. So by using epoxy coated bars, actually, the bridge decks crack a lot because of the lack of bond. So if you use epoxy coated bars, they have to go back, stop the traffic, and you can imagine so much traffic. You need to divert somewhere else, and then they have to seal the cracks. They cannot just leave it without sealing. So each time they seal the cracks, it's $15,000, okay? $15,000, don't convert, just think in terms of dollars, $15,000, okay? So if they're sealing the deck, each time costs $15,000, and in 2 years they may have to do 3 sealants, that's like $45,000, right? So my way of explaining to them is, why don't we spend $20,000 extra dollars up front and not use epoxy coated bars, or use this with epoxy coated bars and avoid those 3 sealing operations, which will save us $45,000. So in the whole scheme of things, we are still saving $25,000 to $35,000. So that's the way you can look at it. It's a different way of looking at the total cost, okay? So so the general perception everywhere, industry, engineers, practicing engineers, everyone will immediately say, oh, that's more expensive. But do the total engineering of the structure, do the total cost of the project, the difference may not be as much as what it appears to be. So that's a problem, but still it's a manageable problem. We'll always have weakness in terms of strength in the transverse direction. You have fiber all in this direction, transverse to the fiber direction, you will always have weaker properties. Okay? And weak matrices, we'll go through some numbers very soon. The matrices are very weak in compared to fiber. Low toughness. This is likely to be most difficult problem to manage. Composites do degrade. Even some, they don't corrode, but there are a lot of problems in terms of moisture. Anytime you have a composite, moisture absorption is a problem, okay? Particularly where there is a lot of temperature. So in cold weather, it becomes cold, it freezes, and then in hot weather, it will unfreeze or it will thaw. So if you have water penetrating your composite and it's sitting inside your composite, when it freezes, what happens to water? It expands, right? And then when it is warm, water will become normal, and then that expansion will cause cracking. So once you have a crack, it will only go one way, which is it will open up more and more. So that's a problem. That's a big problem. There's also a problem with alkaline environment. So FRP bars subjected to alkaline environment can be a problem. Okay, a lot of research has been done in this. In fact, one of my students did a project on basalt fiber reinforced bars, and it's a big problem. Okay, difficulty in connections. How will you connect two composite members? Very difficult. But they are able to do that. In aircraft industry, they have metal inserts. So they will connect the metal parts. So there will be metal insert. You know what an insert is, right? You have inserts inside the composite, and then that can have holes, and you can apply bolts, whatever. So you can connect those using metal inserts, which is possible, but it's a little bit more tricky. And difficulty with analysis. Not everyone can analyze composite material and composite structures. So you have to train yourself to do that. So some learning curve is involved initially. But with proper design and material selection, you can overcome some of these problems. Okay? Okay, so I already talked about this. So many of you are familiar with fiber reinforced concrete, right? So there is a difference between what I am presenting here and fiber reinforced concrete. All right? Fiber reinforced concrete generally has chopped fiber or fiber with small lengths, and it's blended with concrete. Whereas here we will use actual reinforcing bars. We'll show you some samples after some time. Okay, so there's a difference between fiber reinforced concrete and FRP reinforced concrete. So the biggest advantage is this: very lightweight. Imagine picking up this kind of mesh made from steel reinforcing bars. It's highly unlikely I will be able to lift it with one finger. I think she's using one finger or something. Can't see it, but she's doing this. So with one or two fingers, she's able to pick up that mesh. Very, very big difference. Corrosion is a problem for steel reinforced concrete, right? So here even Dr. Das and your group, they are doing very good work on corrosion resistance. So what happens is whenever steel bars corrode, depending on the corrosion product, they will expand. The volume will increase. And because our concrete is very weak in tension, the surrounding concrete will start cracking. Okay? So of course, there is some loss of area in the reinforcing bar, right? Because of corrosion. But that's not a problem. That 2 or 3 or 5 or 6% loss in area is never a problem. It's not a big deal. The main problem is loss of bond.